All right, this is the quiz for Chapter 4B. This is the second half of Chapter 4. This figure shows blocks supported by two ropes. What is the tension in the rope on the right? All right, so first of all, we want to just draw our force vectors. We have a force vector here and a force vector here. I have a force tension and a force tension. Now, because this is symmetrical, that is that because the angles are the same, these tensions are going to be the same. But let's say that we don't do that. So I'm going to call this force tension on the left and force tension on the right. So we'll assume from the beginning that they're different, but then I'll show you when we draw the force vector diagram that they're actually the same. But you might know that intuitively just because I have these angles are identical here, but it works out. So anyway, I've done step one. That's step one where I just draw the force vectors. On step two, I'm going to draw the force vectors on a vector diagram, labeling the angles appropriately. This is 50 degrees. This is force tension on the right. Force tension on the left. This is 50 degrees. If you're not certain about that being 50 degrees, let me show you. If you recall from high school geometry, if I have a line that bisects two parallel lines like that, then this angle is equal to that angle. I think those are called complementary angles, if I'm not mistaken. Or they might have another name, I forget. Anyway, those two angles are the same, so then I know that this angle is the same as this angle right here. And then I also have the weight, which is there. That's step two. In step three, I draw my vector diagram with my resolve vectors. Here I have FTR, that's force tension of the right rope, times sine of 50. FTL times cosine of 50. Here I have, excuse me, not cosine, sine. So the y component. Those are the y components. And then I have down here FTL cosine of 50. Over here I have FTR cosine of 50. And then down here I have FW. Now this is where I can determine that the tensions are the same. If you hadn't already determined that sort of intuitively. If I do my sum of the forces in the x direction, this equals ma. And this is step 4, where I apply Newton's second law. Sum of the forces in the x direction equals ma, but my acceleration is equal to 0. So I sum up the forces on the x direction, FTL cosine of 50 minus FTR cosine of 50 equals 0. And then I can show then that FTL equals FTR. Now, hopefully you don't have to go through that step. Hopefully you can just look at this and say, well, these angles are the same, so these forces are the same. That the tension in each rope is the same on both sides. But that's where it comes about mathematically. Now, I want to do the same for my y direction. Sum of the forces in the y direction equals ma. The acceleration equals 0, so that equals 0. And here, I'm just going to combine these two because these two forces are the same. So I'm just going to say 2ft sine of 50 minus fw equals 0. And then I solve for ft. I add fw to both sides, and I divide by 2 sine of 50. That's mg over 2 sine of 50. It's 23, 9.8 over 2 sine of 50. And that gives me I get 147 or 150 newtons. So the correct answer is A. All right, this figure shows an inclined plane with a block. The block is accelerating up the inclined plane, and the three forces are labeled. Which of the following is an appropriate equation that follows the application of Newton's second law of motion? All right, so let's just go ahead and draw my vector diagram. There's my x-axis. There's my y-axis. Now if this angle, 60 degrees, this angle, It's 30 degrees. So I'm going to draw my resolved vectors. I have Fn, I have F, and then I have my Fw cosine 60 and Fw sine 60. And that's it. So I want to look at these equations. Now, let's see, what is it saying it's doing? So yeah, this block is accelerating up the inclined plane. So the sum of the forces in the x is going to equal ma x, and the sum of the forces in the y will equal ma y. Let's just go ahead and write out the equations just for practice. Although I don't think that's really necessary here, because you can, just from looking at the vector diagram, you can tell which ones are correct or incorrect. Well, let's go ahead and write them out just for practice. All right, so the sum of the forces in the x is going to be F minus Fw cosine 60 equals max. And I know that ax is non-zero because the problem says it's accelerating up the inclined plane. And the sum of forces in the y are Fn minus Fw sine 60 equals may. But I know that ay equals 0, so I can say Fn minus Fw sine 60 equals 0, or I could even go further and say Fn equals Fw sine 60. Now let's compare that with what we have over here. All right, A is not correct because Fn and F aren't even on the same axes. They're on x and y axes, so they're unrelated. All right, here I have Fn minus Fw sine 30 equals max. There are several mistakes with this. First of all, the most blaring one is that I have an ax here, but Fn is the y component. And this is Fw sine 30 is actually the x component of the weight. Let's see, I can make this correct by saying make this 60 degrees and make this into a y, and then that equation would be correct. But as it's written, it's not correct. Fw sine 60 equals Fn. Well, look, that's what I wrote down here. That comes from the sum of the forces in the y direction. So C is the right answer. And then I have Fw equals Fn. Well, that's opposite, or that's contrary to what this says, that the normal force is actually the y component of the weight. So D is not correct. So C is the correct answer. Dock worker loads crates on a ship, finds that a 100-kilogram crate, initially it rests on a horizontal surface, requires 400 newtons to set it in motion, and then 300 newtons to keep it moving. What is the coefficient of kinetic friction? All right, well, you really need to read the problem to find out what's the relevant information here. 300 newtons is my kinetic frictional force. I know that because after I get it moving, that's the force required to keep it moving. My normal force is going to equal the weight because it's at rest on a horizontal surface. So I have this crate. It has a certain weight. And the normal force, since it's not on an inclined plane or an inclined surface, the normal force is equal to the weight. And that's equal to the mass, which is 100 kilograms, times the acceleration due to gravity. I'm just going to call it 10 meters per second squared here. And that's equal to 1,000 newtons. All right. Then I need to say, well, Fk equals mu k times Fn. So mu k equals Fk over Fn, which is 300 over 1,000. Zeros cancel, 3 over 10, which is 0.3. So A is the correct answer. Consider this block. What is the normal force acting on the block? All right, there are no forces acting on this. So I can say, just going to label all my there are forces acting on it. Let's just label the forces. There's my Fw. There's my Fn. And I believe that's it. Yeah, those are the only two forces. So obviously this block is going to be sliding down because it has no frictional forces holding it in place. It's completely smooth surface. But right now I just want to know what is the normal force. There's my x-axis. There's my y-axis. I know that this angle equals 60 degrees. Just to save space, I'm just going to go ahead and draw the x and y components of the force weight. This is going to be the y component, FW sine of 60. And this is the x component, FW cosine of 60. All right. And then if I apply Newton's second law, sum of the forces in the y direction. Actually, let me go back and I'll redraw this. So it's a little more clear. I'm just going to draw the vectors again. So I have the normal force here. It should be on the axis. Fn. I have FW cosine 60. And I have FW sine 60. Now I know what the weight is. My weight of an object is just the mass times the acceleration due to gravity. That's 10 kilograms times 10. That's 100 newtons. All right. And so if I want to find my normal force, I can say the sum of the forces in the y direction equals MAY. But my object is not accelerating in that direction. Acceleration in the y direction equals 0. So I can say the normal force minus FW sine 60 equals m times 0, which is equal to 0. So my normal force equals my weight, which is 100 newtons, times the sine of 60, which is 0.87. Which gives me, let's see, if I keep proper, if I use 9.8 here, it would be 98 newtons. Sorry, I'm going to use 9.8 here. And that gives me 85 newtons. All right. If you use 10, you get 87, but then you would know it would be that number. It's the closest one. All right. Let's see. I think I asked another question on the screencast. I'm going to go and address it here. If I didn't ask it, it's a worthwhile question anyway. What is the acceleration of this block as it accelerates down the inclined plane? Well, in that case, we want to look at the sum of the forces in the x direction. And the sum of those forces, notice there's just one force, and that's that FW cosine 60. And I know that that's equal to MAX. So if I want to know the acceleration in the x direction, it's going to be FW cosine 60 divided by the mass. That's mg cosine 60 over m. My masses cancel out. Is 9.8 cosine 60. Which is a 4.9 meters per second squared. All right, below you see two cases, a physics student pulling or pushing a sled with a force F, which is applied at an angle theta. In which case is the normal force greater? All right, the normal force is greater for case 1. Let me show you why. Say that I have an object, and I am applying a force in this direction, which is what this person is doing in case 1. Then I have other forces. I have my normal force, and I have my weight, and I'll say this angle is an angle theta. Then if I draw my force vectors with my resolve vectors, I have my normal force, my weight, I have my y component of the force, and then my x component of the force. If I do the sum of the forces in the y direction, that's going to equal 0 because it's not accelerating in the y direction. It's going to be Fn minus Fw minus F sine theta equals 0. So Fn will equal Fw plus F sine theta. All right, so my normal force is bigger than my weight by this amount. Now in case 2, this force would be on this axis, on the positive y-axis for case 2, where instead of pushing down, you're pulling up. And then if I were to write the sum of the forces in the y direction, it would look like this. It would be Fn plus F sine theta minus Fw equals 0. And so my normal force would equal Fw minus F sine theta. And notice now my normal force is less than the weight by this amount. we know this intuitively, right? That if you have an object that you're trying to push across the floor and you push down on it, that increases the frictional force. It's more difficult to push because the frictional force is dependent upon the, is dependent upon the normal force. However, if you pull up, it's easier to push because that frictional force, the normal force is decreased and the frictional force is dependent upon the normal force. All right, let that sink in. All right, let's move on. Consider two identical blocks resting on a flat surface and one on an incline. Which case is the normal force greater? All right, with this, we work similar problems here. But in this case, my weight and my normal force are opposite. They're equal and opposite. So for case A, my normal force equals my weight. But here, my normal force is there. My weight is there. So I can break my weight into components, the y component of the weight and the x component of the weight, as we did just a couple of questions ago. And then we can show that the normal force is equal to just the y component of the weight, the y component, which is going to be smaller than this value. So here, if I want to know the larger normal force, is going to be A. Outer space, a bowling ball and a ping pong ball attract each other due to gravitational forces. How do the magnitudes of these attractive forces compare? All right. A couple ways we can look at this. We can look at it from the perspective of Newton's third law, which says that for every force, there's an equal and opposite force, equal in magnitude, but opposite in direction. So if I have a force in this direction, I have to have an equal magnitude force, but opposite direction, which means that the magnitudes of the forces would be equal. So that's C. So we can think about it in terms of Newton's third law, or I can think of it in terms of Newton's universal law of gravitation, which looks like that. That means that the force on mass 1 is dependent upon mass 2. And similarly, the force on mass 2 is dependent upon mass 1. All right, so when you're calculating the force for either mass, they're dependent upon both masses. I talked about this before, right? That if I'm standing on the Earth is pulling down on me with 700 newtons of force. But in a similar way, I'm pulling back on the Earth with 700 newtons of force. So basically, we're all walking around just holding up the Earth, holding up the planet Earth. And we usually think about the Earth pulling us down, but really we're all pulling back up on the Earth. All right. So how do their accelerations compare? Well, my force is equal to the mass times the acceleration. Now I know that they have the same force. However, so the force is the same. However, for the bowling ball, the mass is much bigger than for the ping pong ball. So the bowling ball has a much smaller acceleration. So the bowling ball, very small acceleration. The ping pong ball, very large acceleration. Bowling ball, very large mass, very small mass. And it's because the forces are equal. So since their masses are different, their accelerations have to be different as well. So let's see, accelerations are opposite, that's true, but not bigger for the bowling ball. Here we go. Option D is the correct answer. An opposite but bigger acceleration for the ping pong ball. You tie a rope to a tree and you pull the rope with a force of 100 newtons. What is the tension in the rope? Here's my tree. I have a rope attached to it, and I pull on it with a force of 100 newtons. Pulling on it with a force of 100 newtons. The tension in the rope is also 100 newtons all the way throughout. C. So we talk of war opponents, each pull with a force of 100 newtons on opposite ends of a rope. This guy pulls with 100 newtons, and this guy pulls with 100 newtons. Probably many of you put E, but E is not the right answer. Some of you might even put 0, but 0 is not the right answer. The correct answer is that the tension in the rope is 100 newtons. You might think, well, that doesn't really make sense because I have one guy pulling on one end of the rope and another guy pulling on the other end of the rope. Their forces must add up in some way, or they must cancel out in some way. Well, think about the tree. I think this is probably a little more intuitive with the tree, but you know what? Just replace the tree with a guy that doesn't move, and it's the same thing. Right? So the force is exerted by the tree is also 100 newtons, but it doesn't change the tension in the rope. So you have 100 newtons of tension in the rope in both of these cases. Z is the right answer. All right, you and a friend each pull with a force of 20 newtons. If you want to rip a rope in half, then what's the best way? All right, the best way to do this, if you can apply a force of 20 newtons on both ends of the rope, is not A, because if you do that, you're just going to get 20 newtons of tension in the rope, but is B, to tie the rope to a tree, and then you both pull from the same end. So if you both pull, you're going to get 20 newtons and 20 newtons. So you'll get a net force, or tension, of 40 newtons. Box sits on a pickup truck, frictionless truck bed. When the truck accelerates forward, the box slides off the back of the truck. This box has a certain amount of inertia. Box has a certain amount of inertia. It doesn't want to move because of this inertia, this quality that it has that's intrinsic to the mass. However, when the truck moves, unless there is a force acting on the box is just going to stay where it is and it'll slide off the back. Now, usually this doesn't happen because we have a force. We have the kinetic frictional force. Right. So in this case, the reason it didn't move is because no net force acted on the box. If no net force acts on the box, it's not going to accelerate. It's just going to stay where it is. So C is the right answer. Anti-lock brakes keep the car wheels from locking and skidding during a sudden stop. Why does this help slow the car down? It's because static friction is better than kinetic friction, or what's called here sliding friction. Static friction is better, and in particular, we mean that mu s is almost always larger than mu k. So that is option number C, that mu s is mu k, or not say, I'm sorry, D is the correct answer. Static friction is better. This is also this is anti-lock brakes. It keeps your tires from locking up, because when your tires lock up, it's not static friction that's at play, it is the kinetic friction. That might not make sense to you, but think about the surface of your tire with respect to the surface of the road. They're stationary as long as the tire is stationary to the road, as long as the tire is rolling. It's not until the tire stops rolling that the car begins to skid, and then that kinetic friction begins to come into play. All right, your sister wants her to give you a ride on her sled on a level ground. What is the easiest way to accomplish this? We talked about this before in a previous question, but when you pull up, it decreases the normal force, which decreases the kinetic friction. Remember, because friction is proportional to the normal force. So in option 2, or scenario 2, is the best way, because that decreases my kinetic friction because the normal force is decreased. And we saw that in a previous problem, the way the force vectors are involved. All right, box of weight 100 newtons is on a rest where the coefficient of static friction is 0.5. A rope is attached to the box and pulled horizontally. Which way does the box move? Oh, let's see. I have two different numbers here. Well, it doesn't really matter. Let's just say that this is 0.5, like it says up above. I want to know which way does it move. Well, let's figure out what is the maximum static friction. Fs max equals to mu s times my normal force. In this case, my normal force is equal to the weight because it's on a flat surface. So my normal force is 100 newtons, mu s is 0.5. So my static frictional force is 50 newtons. That means that I need to apply a force of at least 50 newtons in order to make this object move. However, I'm only applying a force of 30 newtons, so it's not going to move. So the answer then is that the box does not move at all. Box sits on a flat board. You lift one end of the board, making an angle with the floor. As you increase the angle, the box will eventually begin to slide down. We saw this in the previous online quiz, where if I increase the angle theta, that decreases my normal force. If theta goes up, my normal force goes down. If my angle theta goes up, my normal force goes down. That means that my kinetic or my static friction is also going to go down. All right, so that's one thing, is that the normal force will be decreased, and that will cause the static friction to decrease as well, which will cause the block to move down because there will be less of a frictional force holding it in place. Now, you might be inclined to put B, but B is not correct because the coefficient of static friction doesn't decrease, only the force due to static friction. Now let's look more closely at option A. The component of the gravity force parallel to the plane increases. I'm going to draw these force vectors of my normal force there and my weight here. As I increase theta, that means that this angle will decrease. I'll call this angle phi. As theta increases, phi decreases. And so more and more, as theta increases, I get a larger and larger component of the force weight in the x direction. Let me write that in words. So as theta increases, phi decreases, and the force weight in the x direction decreases. That's going to cause it to accelerate in the downward direction. You probably know this intuitively. Like if I make this inclined plane move up and up, the object here, this force due to the weight in the x direction, is going to get bigger. And that comes about because of the way the angles work, that the cosine of a small angle is bigger than the cosine of a big angle. All right, so the answer here is A and C are option D.